a consumer with the utility function u is equal to xy cubed, subject to two constraints. We have a budget constraint, x plus y is less than or equal to 50, and we have a coupons constraint, 2x plus y is less than or equal to 60. Now, our two constraints are inequalities, they're less than or equal to, so I can use the Kuhn Tucker approach. So I'm going to use the Kuhn Tucker approach and set up my Lagrange equation, which is going to be a function of x, y, and we have two constraints, so I have lambda 1 and lambda 2. So the function I'm trying to optimize is my utility. So that's going to be x, y cubed plus lambda 1 times my constraint 1, which is going to be 50, the budget, minus the x plus y, so it's going to be minus x minus y. And then I have my second constraint, so I have lambda 2 times, this time the budget is 60, and the constraint is 2x plus y, so this is going to be minus 2x minus y.
Now I'm going to show you a slightly different approach than what I did in the previous examples. Before I start looking at which constraint I'm assuming is true, I'm just going to do the derivative of the Lagrange function with all of the different variables.
So with respect to x, the derivative becomes, for the first term here, the derivative is going to be y cubed. For our first constraint, this is going to be minus lambda 1. And for our second constraint, it's going to be minus 2 lambda 2. Doing the derivative with respect to y, for my first term here, I get 3xy squared. For the first constraint here, the derivative becomes minus 1 times lambda 1. For the second constraint here, I have minus 1 times lambda 2. I have the derivative with respect to lambda 1. This is my only lambda 1 term, so the derivative becomes 50 minus x minus y. I have the derivative with respect to lambda 2. The derivative of that becomes 60 minus 2x minus y. So there are all of my first derivatives. Now what I'm going to do to solve this, I'm not going to try to solve all of this together. I'm going to use the Kuhn Tucker approach, and I'm going to assume one of the constraints is naturally satisfied. Which constraint do you guys want to assume is naturally satisfied? Okay, so we're going to assume constraint 2 is naturally satisfied. Thus, lambda 2 will be equal to 0. Constraint 2 naturally satisfied. So what happens when we do that? I have constraint 2 would be naturally satisfied, so lambda 2's would all be equal to 0. And now I'm going to set up my system of equations. So I'm going to set all the derivatives to be equal to 0. So 0 will be y cubed minus lambda 1. 0 will be equal to 3xy squared minus lambda 1. And 0 will be equal to 50 minus x minus y. And this last derivative wouldn't exist because lambda 2 would be equal to 0. So now I'm going to solve this system of equations. So from the first equation, I have lambda 1 is equal to y cubed. From the second equation, I have lambda 1 is equal to 3xy squared. So I can set my lambda 1 to be equal to my lambda 1. So this is going to be y cubed is equal to 3xy squared. So now do you want to isolate x or do you want to isolate y in this equation? Let's isolate x. So I'm aiming to isolate x. So I'm going to divide both sides by 3y squared. I get x is equal to y over 3. Now what I'm going to do is I'm going to substitute this into my third equation. So I get 0 is equal to 50 minus my x value of y over 3 minus y. So this gives me 50 minus 4/3 y. Remember that this is 3 over 3y. So then moving my 4/3 y over to the other side of the equation, I get 4/3 y is equal to 50. Multiply both sides by the reciprocal. I get y is equal to 37.5. And I'll also be able to solve for my x value because x will be equal to y over 3. So that's going to be 37.5 divided by 3, giving me 12.5. So now I have an x and a y value. What do I need to do before I accept this as my final answer? I have to test it. I have to test and check my assumption. I can't just continue to assume that it's going to be naturally satisfied without testing that. So what I'm going to do is I'm going to grab my constraint 2. 2x plus y is less than or equal to 60. Check constraint 2. 2x plus y is less than or equal to 60. And I'm going to sub in these x and y values. So this should be 2 times 12.5 plus y is 37.5 is less than or equal to 60. And this gives me 62.5, which is not less than 60. So constraint 2 is not satisfied. So what do I do next? I'm going to try to assume that the other constraint would be naturally satisfied. So now I'm going to do this differently. I'm going to assume lambda 1 is equal to 0. In other words, constraint 1 would be naturally satisfied if constraint 2 is met, or constraint 2 is binding, not constraint 1. So now I'm going to go back to my derivatives over here. So I'm setting constraint 1 to be equal to 0. So now this would be 0, this would be 0, and this wouldn't exist. I'm going to set these derivatives to be equal to 0. So from our first equation here, I have 2 lambda 2 would be equal to y cubed. Therefore, lambda 2 is equal to y cubed divided by 2. From our second equation here, I have lambda 2 is equal to 3xy squared. So now I set lambda 2 is equal to lambda 2. I have from the first equation, y cubed divided by 2 would be equal to, from the second equation, 3xy squared. Let's go about this trying to isolate x or y? X. So let's isolate x. So I'm going to divide both sides by 3y squared. So then I get x is equal to y over 6. So now I'm going to substitute this into my third equation. I get 0 is equal to 60 minus 2 times my x value. I'm going to do the substitution to give it y over 6 minus y. This gives me 60 minus 1/3 y minus 3/3 y. 0 is equal to 60 minus 4/3 y. Moving this over to the other side of the equation, I have 4/3 y is equal to 60. Multiplying by the reciprocal on both sides, I have y is equal to 45. And I can solve for the corresponding x value because x is equal to y divided by 6. This will be 45 divided by 6. I get 7.5. So now, before I settle on this being my solution, what do? I have to do another check. So this time I have to check that which constraint did I assume was satisfied? Constraint 1. So I have to check constraint 1. So constraint 1 going all the way up to the top is x plus y is less than or equal to 50. So I'm going to take that equation, bring it down here, and substitute in my x and y values. So I get 7.5 plus a y value of 45. Is it less than or equal to 50? Well, this gives me 52.5, which is not less than or equal to 50. So this is no good as well. So now what do I do? It doesn't work when I assume constraint 1 is naturally satisfied or when constraint 2 is naturally satisfied. So in either words, it doesn't work when we just look at one of the constraints being binding. So now we're going to look at both constraints being binding. So both constraint 1 and constraint 2 are binding. So to solve for this, I focus on those constraints. So I take both my constraint equations right here. Constraint 1, x plus y is less than or equal to 50. And constraint 2, 2x plus y is equal to 60. Sorry, less than or equal to 60. Instead of using inequalities, I'm going to change these to be equal. And so now what I'm going to do is I'm going to solve this system of equations. So for the first equation here, I have y is equal to 50 minus x. For the second equation here, I can substitute that in. I'll have 2x plus y is 50 minus x is equal to 60. So this gives me 50 plus x is equal to 60. I get x is equal to 10. The corresponding y value will be y is equal to 50 minus x, which will be 50 minus 10. Y will be equal to 40. So I have my optimal x value and I have my optimal y value. Questions? Okay, earlier in this question, if we had done this and say this constraint wasn't 60, imagine for a moment, if you would, that this was 65. Then this would have been satisfied and we would have said, we would have stopped right there. We would have been done the problem. We would have said y is equal to 37.5 and x is equal to 12.5. And then we would also say that constraint 1, because we had done this using constraint 1 and assuming constraint 2 is naturally satisfied, we would say constraint 1 is binding. If you can optimize with one constraint and the other one is naturally satisfied, you're in a good position and you leave it at that point. You can't just jump to the end and solve this way. It won't necessarily give you your ideal answer. So what this would look like graphically is you would have one constraint, you might have another constraint. What happened in this problem was we had a utility that was optimized over here. It didn't solve for both. But then when we optimized it, that's a poor diagram, sorry. 1 second. Come on, pen. Imagine if we have a utility like this. And it's easier if I draw this constraint line after. So if we optimize and we get this x, y value, then constraint 1 isn't satisfied. If we optimize over here, constraint 1 is satisfied, but constraint 2 isn't satisfied. So then we had to go to where the intersection would be for those two, which was a little bit lower. Now, sometimes what happens is something like this. So we optimize our utility based on this constraint, and we get a value over here. Now, where optimal is the highest a utility that would work for constraint 1 or constraint red, and it also satisfies constraint 2. So we're happy, it satisfies both. But if we were to use this point of intersection, we would actually end up with a lower maximum utility, optimal utility. So you can't just jump to the intersection because it will end up lowering the utility. It won't always work to solve with both constraints. That only is optimal if the first two scenarios don't work for both constraints. So in this image here, you can see that both constraints are met. Now, when we use terms like binding, it's one of those terms that does get used incorrectly. Meeting both of these constraints is different than one of them being binding or both of them being binding. But I think we can appreciate how that language can sometimes be used incorrectly, as the XY values qualify to meet both constraints. But when we refer to binding, it means that the final solution, that optimal value, will be at that place where both constraints are governing, are limiting.
So in this image that we're seeing here, we can see that we just touched that red line with our utility. So constraint 1 is the one that's binding, and we're below constraint 2. So constraint 2 is naturally met when constraint 1 is binding. Now, in the example that we just did, we could see that we tried constraint 1 being binding and lambda 2 being equal to 0. That didn't work out. We tried constraint 2 being binding with lambda 1 being 0. That didn't work out. And eventually we had to set our solution for where the two constraints intersect. That's when we have both constraints binding. We had to use both constraints. We couldn't assume either of them had a lambda that was 0, and that defined both constraints being binding.